So welcome to this video on multiplexers and demultiplexers. We're going to show you how to create a 2-to-1 multiplexer and a 1-to-2 demultiplexer, and then we'll get a little bit more sophisticated with a 4-to-1 multiplexer and 1-to-4 demultiplexer. We're going to design them and we're going to implement them and test them using Proteus. A multiplexer or MUX is a circuit that acts as a selector switch between two or more channels. In telecoms, we use them to concentrate multiple users' data into a shared transmission channel to reduce the amount of copper lines to a telephone exchange. The data will be binary strings from phone calls and internet traffic. We use multiplexers with demultiplexers to separate the data back out into the individual connections at the receiving end. Only one multiplexer user data or channel is transmitted at a time, but in real life we switch between the channels so fast that there's no loss in data at the other end. This is a 2-to-1 multiplexer. For a 2-to-1 MUX, we have two input logic levels or data channels connected to one output, which we can call Q. The switch-in is controlled by a channel selector switch or logic level, which I've called S. This simple circuit is asynchronous, which means all changes happen immediately when the channel selector state is changed or when the data changes state. We design a circuit based upon the truth table that we want. When the channel select signal S is low, let's connect or transmit data channel A. When S is high, let's connect data channel B to the transmission line, and we can derive the simple Boolean expressions for the transmission line output that we call Q. This will give us the logic gates that we need. Remember that we don't care whether the user data is low or high when we transmit it. We just transmit it anyway. The transmission line could be copper wire, fiber optic cable, radio or microwave link. The transmission line output Q equals not S and A or S and B. This shows us how the logic came about for the circuit. Let's build a 2-to-1 MUX using Proteus. So I've made a new design on Proteus. We'll go to component mode, double click. We'll search for AND_2, which is a generic 2-input AND gate, an OR_2, which is a 2-input OR gate, a NOT gate or inverter. We need a logic state to provide ones and zeros, and we need a logic probe big to see what logic outputs are or inputs. Get some logic states for the data on channel A and channel B and for the selector switch. Just rotate that selector switch a bit and move it. The NOT gate to get not S. That's S, and this will be not S. AND gates for the Boolean expressions for Q. Wire up data channel A and data channel B. Connect not S for channel A and S for channel B. We need a 2-input OR gate for the Boolean expression for Q, the output or transmission line. And we need a logic probe for the output Q to see what logic level it's at. Then we can simulate. At the moment, channel A is selected because S is low. So as we change the state of channel A, Q copies it asynchronously and immediately. And channel B has no effect because we're not transmitting that. Then when we change the select switch to logic 1, it's looking at the data on channel B, not channel A. So it works well. I'm going to go into generator mode and get some digital clocks to simulate the data on channel A and channel B. There's channel A's data, there's channel B's data. Get rid of the logic states because the logic will be whatever the clock is at the time. And I'll automate the channel select as well with a slower clock signal. Get rid of that logic state because the clock will drive the selection and the data. Get some logic probes to look at what the selector signal is and the data from the clocks on channel A and channel B. I've made channel A the frequency of 0.5 Hertz, and data channel B I'll make 3 Hertz and switch it nice and slowly at 1/8 of a Hertz. So when the selector is low, it's channel A that's being transmitted, and when the select goes high, channel B is being transmitted. Low again, so it's channel A. Then select goes high and transmits channel B. The demultiplexer. We need a 1 to 2 demultiplexer, one input being split into 2 output channels. The transmission line output from the multiplexer is now the demultiplexer input signal Q. We separate the transmission data stream into the separate user channels data A and data B. In real life, it's important for the channel select to be synchronized with the channel select for the multiplexer to avoid mixing up the data channels. The truth table looks like this. When S is low, the data incoming on Q becomes channel A, and when S is high, the data on Q becomes channel B, whatever that data is. We can design a circuit from the truth table. We see that data A equals not S and Q, and data B equals S and Q. We'll make the output channels low whilst they're not selected. So I'll select and copy to clipboard the multiplexer because it's very similar to the demultiplexer. Get rid of the OR gate because there's no OR expression for the demux. I'm getting rid of the data logic state because I'm going to just have one logic state, which is the Q transmission line, which is fed into both channel A and channel B expressions for the demux. Got channel A and channel B outputs. I need a logic probe for both output channels, so I'll just wire those up. And now we can simulate the demultiplexer, a 1 to 2 demux. So as Q goes high and low, when the select signal is low, the data goes to channel A. And when the select signal goes high, the data on Q goes to channel B, just like we wanted. So now I will automate the demultiplexer using some clocks in the same way under generator mode, digital clock or declock. So this will be the incoming data for the demux. So I'll get rid of that logic state. And a nice slow selection switch on-off clock of about 1/8 of a Hertz. Get rid of that logic state. 125 millihertz or 1/8 of a Hertz. And the data can be anything really. We want to be able to see it change though. I'll keep that at 1 Hertz. Get some logic probes for the selector switch state and the data. And simulate. So now the selector is low, so it's channel A that's getting the data received. And when it goes high, it's channel B that gets the received data. So here's the two circuits, 2 to 1 mux and a 1 to 2 demux, and we can put them together. So we have a slow clock changing the channel select logic value on the mux and demux. We have some data on channel A and data on channel B. Then the 2 to 1 mux, the transmission line Q, and then the select signal is being copied over to the demultiplexer. Then we have the channel A output and channel B output. So let's simulate this. So when S is low, it's channel A that's being transmitted and received. And when S goes high, it's channel B that's being transmitted and received. So we have a 2-to-1 mux and a 1-to-2 demux working synchronized. So channel A and channel B, this could be in one city, this could be on the other side of the world, and the two channels are connected to each other, which is why we make these in the first place. So we're going to build upon our 2-to-1 mux and 1-to-2 demux, and we're going to control 4 channels A to D. And to control 4 channels of data, we need 2 selection bits, which I've called S and T. So as S and T are changed from 00 to 11, channel A will be transmitted and received through to channel D. When TS is 00, channel A goes to Q, then back to channel A on the demux. When TS is 01, it's channel B. When TS is 10, it's channel C. And when TS are both high, it's channel D that's transmitted and received. I've included a really simple 2-bit ripple counter to control S and T, and I've created a 4-bit ripple counter just to provide some data to automate the data. This ripple counter will just count up from 0000 to 1111 and give us different frequencies for our data. So this is the truth table that shows us how we derive the logic for the 4-to-1 mux and the 1-to-4 demux. As TS goes from 00 to 11, it's channels A, B, C and D that are related to Q, the transmission channel. This is a Proteus schematic. I've provided some wire labels. For instance, not T is called NT, not S is NS. And I've got data A, B, C and D. And this is how we will do it when we make it on Proteus. On the left is the 4-to-1 mux and on the right is the 1-to-4 demux, controlled by 2 select signals, S and T. So let's build the 4-to-1 mux on Proteus. We're going to need some components. We'll need 3 input AND gates, and we're actually going to need some 4 input OR gates rather than 3 as I've shown here. We'll need logic states as usual and logic probes to see what logic levels wires are at. I've used some buffers just to make sure there's enough juice. So this is to provide S and T, the selection switches. I've got T, not T, S and not S with Y labels. This will be for channel A, which is not S and not T, then channel B, and so on. If you look at the truth table earlier, this is where the logic came from. And the output of this 4-input OR gate will be the transmission line Q. Put some logic states in. And these 4 logic states form the data channels A to D and a logic probe for Q. So when TS is 00, it's channel A that's transmitted and received. When TS is 01, it's channel B, and so on. When TS is 10, it's channel C that's transmitted. And when T and S are both high, it's channel D that's transmitted. We'll do the same at the other end with a 1-to-4 demultiplexer. So we've got T and S, and we've got Q, the received transmission line coming into the demux. We need some 3-input AND gates for each channel on the demux, channel A to D. They all are connected to Q. If you look at the Boolean expressions from earlier, have some logic probes. Then we have not S, not T for channel A. Channel D has T and S both high. As we simulate, T and S are both low, so it's channel A that will receive the data, and this is the data. When TS is 0, 1, it'll be channel B that gets the data. When TS is 1, 0, it's channel C. And when T and S are both high, it's channel D that gets the received data in the demux. So we can simulate, and at the moment it'll be the data on channel A that would be transmitted. Any data on channels B, C or D would have no effect. They wouldn't be transmitted or received, as we can see. Then select channel B. So A has no effect, or the other channels C and D, but channel B is now being transmitted and received. Then channel C. So channel A has no effect, B has no effect, but channel C is transmitted and received. Then finally we select channel D. None of the other three channels will have any effect, but channel D will be transmitted and received. So we've got our 4:1 mux and 1:4 demux. Channel A is being transmitted and received, and channel B, channel C, then channel D. So there's a full circuit of the 4:1 mux and 1:4 demux that's been automated by a 2-bit ripple counter for the select. So there's the counter providing us some data. We could have just used clocks. There's the 4:1 mux, and there's the selector 2-bit ripple counter just to provide the count for the selector, and then the 1:4 demux. And there's the whole circuit. As we simulate, you can see what's happening. The selectors are counting from 0, 0 to 1, 1 to transmit channel A, then channel B, then channel C, then channel D. A, B, channel C, and channel D. Got a nice slow clock to control the select. The data is random. You can have any data on any channel being transmitted and received. So thanks so much for watching this video. I hope it's been useful. Please like and subscribe, and importantly, place some comments below so that I can answer your questions. All the best.